In this lecture, we're going to solve some of the problems based on the chapter 9 and 10 from the textbook. This one, Baldi and Murray. And then we're going to solve this problem. So let's look at the first one. So 9.34 is regarding the osteoporosis, and they have given the question stem and asked us two different sub questions to calculate the risks and odds of two conditions. One is osteopenia and another is osteoporosis. So and odds, risks and odds for osteopenia and porosis. So if you read the question stem, they have given us the probability that it is 0.40 that the woman chosen has osteopenia. So that is nothing but probability of openia. That's 0.40. So if you understand the risk, so risk is just the probability of that particular event, or in health field, that's the probability of that particular disease. So that is nothing but the risk of osteopenia. So that's why your risk is just the probability of that condition. Openia 0.40. Simple. Then odds of any condition or event is probability of that particular event occurring upon probability of that event not occurring. So that is probability of A divided by probability of not A. So probability of A in this case is osteopenia, because we are looking at osteopenia. So that will be probability of osteopenia upon 1 minus probability of osteopenia. Right? Because we are saying that it could be anything but not osteopenia. That's why we are dividing it by 1 minus probability of osteopenia. And then you just have to substitute the given value of 0.40. So that will be 0.40 upon 1 minus 0.40, and you're going to get this probability as the odds. So that is the odds of osteopenia. Okay, 0.667. Now similarly, you can follow the same steps now for osteoporosis. That is the another condition. So probability for that is given as well in question stem. So if you look carefully, 0.07 is the probability for osteoporosis. So probability of osteoporosis is nothing but 0.07, and that probability is nothing but the risk of that condition. That's why risk of osteoporosis is nothing but the same probability. Odds again is the probability of osteoporosis upon 1 minus probability of osteoporosis, and you just substitute that those values, 0.07 divided by 1 minus 0.07, and if you solve that, it will be somewhere around 0.753. So that is pretty simple question from this chapter. And now let's look at this 10.3. So before we go into detail of the solution, let me just rub this thing. So question stem like that, this could be also asked in probability chapters, or I think it's very important to derive what probability is given, what probability is asked in question stem by reading through the question stem or even some article or something like that. So let's look at this one. According to 2003 report of US Health Resources and Service Administration, co-infection of HIV. So we are talking about two infections occurring together. That's why co-infection. Co-infection of HIV and hepatitis C, that is HCV, is on rise. Only about 2% of Americans have HCV, but 25% of Americans with HIV have HCV, and about 10% of Americans with HCV also have HIV. So question stem like this will be given to you sometimes, and then you might have to derive some of the probabilities. So sub question A says Write the information provided in terms of probability. Are the two virals independent or not? So we have to test whether the events are independent or not as the sub question of A. But first we have to just derive the information given and write it in terms of probability. So if you look at this one, this sentence, only about 2% of Americans have HCV. Okay, and then the next segment is for different percentage. So if you look at only this part, it tells us 2% is what? That's what we have to derive. So 2% of Americans have HCV. So simply that's nothing but probability of having HCV or getting HCV is 0.02. 2%, 0.02 probability. Now let's look at the second segment of this sentence. But 25%, now this is another number or quantity, of Americans with HIV have HCV, right? So basically, if you try to split these events, so before we even dive, so this is, you can see that there is some conditional probability. We know that these two infections are occurring together, so there is like some overlap in these things. And then we always write conditional probability, something like probability of B given that A has already occurred, right? So in that case, I like to say that A is kind of condition and B is kind of specific event, right? So you can think of this, and I think that would help you derive some of this probability from the question step. So let's give it a shot here. So it says 25% of Americans with HIV. So basically you're imposing a condition that those has to be with HIV. So that is like your condition, have HCV. So basically with HIV is your condition and your event of interest, or I would say specific event in this case, is HCV. So this is like your A in this case, and A, B in this case is HCV, and that is 25%, so 0.25. So probability of HCV, specific event on top, given that HIV has already occurred. So given that this condition fulfills, and that is nothing but 0.25. 25% is 0.25 probability. And the last portion, it says 10%, this is another quantity, of Americans with HCV also have HIV. So again, this condition is with HCV, so you have to have HIV to qualify for this number. So that's the condition. Have HIV, so that means that's a specific event in this case. So you're going to write it as probability of HIV given that HCV has already been occurred, right? And that is nothing but 10%, so 0.110. So that is all the information given to us. So we have completed the first subtype of this problem. Second is looking at whether the events are independent or not. So to test whether two events are independent or not, we can simply say that this rule should be valid. So for example, probability of B should be equal to probability of B given A has already occurred, or probability of B given that A has not already occurred. So all of them has to be equal to probability of B or the same, right? So in conceptual meaning, we are saying that it really doesn't matter whether A has occurred or not occurred, the probability of B remains same, right? In that way, we can say that B event is particularly independent of A. In other words, both A and B are independent events. So if we could prove that this is true, then we can say that these events are independent. If not, we're going to say that those are not independent. So let's test that. So in this case, our probability of A would be probability of HIV or B, either way it doesn't matter. And then probability of another event would be probability of another event given that HIV has already occurred. So let me just stick to this. Um, so if we consider the HCV as B, event B, and we know the probability of HCV is 0.025, that's 0.025, right? So we are going to compare that. So that's probability of HCV we got. Now we have to test that if probability of HCV equals to probability of HCV given that HIV has already occurred. And we are using this specifically because we already have that in the data, right? So you always want to see what you have and then how can you proceed with the proof. So we know that we do have this information, we do have this information as well. So we can simply compare them. So this is the part we have, and HCV given HIV is this particular part in this formula. So this formula. So we know that this is 0.02 from here, and probability of HCV given HIV, that's also given 0.25, 0.25, and both these probabilities are not equal, right? So that's why we say by this rule, so by this rule, A and B are not independent, or in other words, HCV, HCV and HIV are not independent. Okay. So that is about this A part. Now go for the B part. So B is asking what is the probability that randomly chosen Americans has both HIV and HCV. So basically it's asking probability of HIV and HCV, right? And there are like several probability rules for, that these are different for and or, and then within and or there are also like little bit different or variations of rule based on whether the conditions are independent or not. We know we already proved that these events are not independent. That means there is some dependency. That means there will be this conditional um, portion existing in this probability for rules that we are going to use. Um, so let's look at that. So probability of HIV and HCV is by formula probability of HIV times probability of HIV given that HCV has already occurred. So if you go back and look at general rule says that probability of A and B is equal to probability of A times probability of B given that A has already occurred. And that is true for not independent events. And we are going to use that because we already proved that our events are not independent. If in case we have all we have proved that it's those are A and B or HCV and HIV are independent events, then we would have used another rule, that's probability of A and B is simply probability of A times probability of B, and is for multiplication, just notice that, and we simply multiply those two probability because there is simply no dependence, so they are independent. But for this question we already know these are we already proved that these are not independent, so we are going to use this particular rule. So just write it that. So I've already written it here. Probability of HIV, HCV and HCV is probability of HIV and probability of HIV given that HCV has already occurred. Now go back and see in your data what is given, right? This is the given information from your question stem. Do we have HIV probability? It doesn't look like, right? We have HCV as single event. So basically, we cannot derive it, and precisely we cannot derive it because if you read the question stem, we do not know whether these are the only two events because there could be several other events occurring, right? So we cannot derive that particular other probability as 1 minus probability of another one. That can be done only when these two events are existing as total sample space. But we don't know. It could be sample space at CV, HIV, CV, HIV, and maybe some other conditions as well. So we do not know. So we cannot derive that particular information. But if you think conceptually, if the two events are having some dependence and we are looking for this and if you draw this Venn diagram, HIV, HCV, and means this particular intersection, right, that we are interested in. So it doesn't really matter whether you consider HIV and HCV or HCV and HIV, you're going to get the same answer of probability for that intersection or the and. So let's flip it around for that limitation of given information, and let's write that this is also nothing but equal to probability of HCV and HIV. And for that, if you apply this rule again, that will be probability of HCV times probability of HIV given HCV has already occurred because it's B over A. Um, and then you just have HCV from here 0.02, that's 0.02. HIV, oh, given that HCV has already occurred, HIV given that HCV has already occurred, that's 0.10. And then you just multiply and do simple math. You should be able to get somewhere around like this. So that's how you calculate the probability of and of two events which are not independent. And similar thing you can practice for independent events. That will be just multiplication and that would be easier. So let's move to the 10.3 spinal cord injuries, and it's the data for state of Florida report that 75% of all patients first diagnosed with spinal cord injuries are male. That's the given information. And in the part A, they are asking what is the probability that next two patients diagnosed with spinal cord injury in Florida will be male. So let's just derive that, okay, this is the number given to you, 75% diagnosed with spinal cord injury are male. So we know that probability of being male is 0.75. The reason I have written this first part because in A subtype they are asking us probability that next two patients diagnosed with spinal cord in Florida will be male. So we have to consider those sequence. But for simply we just say that probability of, let me just write it, probability of getting male will be, a randomly given person being male is 0.75. So now let's look at the question again. Subtype A, it says what is the probability that the next two patients diagnosed with spinal cord injury in Florida will be male. So in that case we have to think about a probability of subsequent events, right? So there are like several examples of picking up frog from pond in the textbook for the subsequent event. So let's look at that. Let's say there are 10 male frogs in pond and 10 female frogs in a pond. Oops. And if you want to draw randomly a frog, what is the probability that that frog will be, first frog will be male? If you are interested in that particular property, that will be 10 because there are total 10 males, and over 20 because there are total 20, 10 plus 10, right? But now you say, let's say you have kept this frog aside, or first frog aside, so you're not putting it back into the pond, and then you are drawing second frog. Then probability of that drawing second frog, drawn second frog being male, will be now 9 over 19, because you have already lost one out of the total pool, right? But that is true generally for smaller samples like this, 20 frogs or so on. But if you are looking at larger samples, such as the state of Florida, like this in question, we say that if we derive these two probabilities of first being was 10 over 20 and then second doing was 9 over 19, and if you know, there will be some minute difference, but for larger sample these two probabilities will approximately will be equal. So for large sample, we consider these events occur as independent events. So basically they occur independently. Right. So that is like we have to make an assumption, but only when we have the larger sample. So in this case, we have the state of Florida. So right away we know that that's the larger sample. So we can consider these next two patients, probability of getting first patient male and probability of getting second patient male, these two events, we consider them as independent events. That's why probability of getting next to patient male will be probability of first being male times probability of second being male, because that will be AND probability, right? So AND, we do multiplication. Probability of first being male will be same as this one, 0.75, and even for probability of second, it's going to be same because we assume that these two events are independent for a larger sample like this. So we just multiply them and we are going to get the answer somewhere around this, and that's nothing but the probability.